So, welcome to module 21. In this module, we will introduce the concept of independence of random variables. So, we have the following setup. Suppose x is a random vector x1, x2, xp, and these are p dimensional random variable with joint distribution function fx. And suppose fxi is the marginal distribution function of xi. Then we have seen that to get the marginal distribution function, I have to take the arguments of unwanted variable to infinity. So, fxix would be same as I look at the joint distribution function, and the unwanted variables are all xj's which are different from I take them to infinity. So, this is what gives you the marginal distribution function of xi. So, now I introduce the definition of independence of random variables, which is in some sense similar to the concept of independence of events. So, I will say that these random variables x1, x2, xp are independent if I take any sub collection of this x1, x2, xp. So, call that sub collection as x lambda 1, x lambda 2, x lambda q, where q is from 1 to p. These are sub collections. So, lambda 1, lambda q has to be a subset of 1 to p, because the indices of x1, x2, xp are 1 to p. So, I will say that this is independent if for any sub collection, if I look at the joint distribution function of this sub collection of random variables, that is same as the product of individual distribution functions. Now, this is the situation when you have a finite collection of random variables. Now, sometimes you may have infinite number of random variables or infinite collection of random variables. So, let us x lambda belonging to lambda be a family of random variables. So, this is an arbitrary collection of family of random variables, which may be a countable collection, which may be uncountable collection. So, it is an arbitrary collection of random variables. I will see that the random variables in this family are independent if I look at any finite sub collection of this family, and the random variables there are independent. So, I will say that random variables in a collection of random variables are independent. If you look at any finite number of them, they are independent. So, few quick observations. Suppose the lambda 1 is subset of lambda 2, where lambda 1 and lambda 2 are index sets. Then x lambda belonging to lambda 2 are independent. If suppose they are independent, then x lambda belonging to lambda 1 are also independent. Note that this would be a larger family of random variables, this would be a smaller family of random variables. So, what this remark essentially says that if larger family of random variables are independent, then the random variables in the smaller family are also independent, and that is obvious, because when I look at any sub collection in this smaller family, that is also a sub collection in the larger family. So, the joint distribution function would be same as the product of marginals. Now, another remark which says that the above definition can be extended to random vectors in an obvious manner. So, for example, if x1, x2, xp is a random vector which is p dimensional, and suppose it has distribution function f. Suppose I have another random vector y1, yq which is q dimensional, and suppose this has distribution function g. And suppose z is the joint collection of x and y, which is x1, x2, xp and y1, y2, yq. So, it is a p plus q dimensional random variable. And suppose the distribution function of this is h. Then x and y are said to be independent if and only if I look at their joint distribution function is same as the product of the individual distribution functions. So, the above definition which I gave for random variables in R1 can be easily extended to the case when we are talking about independence of random vectors. So, now let us try to see how to check whether a given set of random variables are independent or not. So, it says random variables x1, x2, xp are independent if and only if look at joint PDF of the whole collection of random variables is same as the product of marginal distribution functions. Note that by definition x1, x2, xp would be independent if and only if the joint distribution function of any sub collection should be same as the product of integers. But this result somehow simplifies our life. It says you do not have to check that condition for all sub collections, we just check it for the complete collection. if our complete collection joint distribution function is same as the product of marginals, then you can conclude that x1, x2, xp are independent, and this condition is if and only if. So, if it happens they are independent. If this condition is not satisfied, then x1, x2, xp will not be independent. Note that this was not the situation when we are talking about independence of events. When we are talking about independence of events, I had to satisfy the probability of joint occurrence as same as product of individual occurrences for every subcollection. But in the case of random variables, independence can be easily concluded by checking whether the joint distribution function of the complete set is same as the product of individual distribution functions or not. So, let us try to see the proof. Suppose that x1, x2, xp are independent. Then clearly for every subcollection this holds. So, in particular for the whole collection the one would hold. So, one way is obvious. Now, conversely suppose one holds, then I have to show that x1, x2, xp are independent. For that I have to show that if I look at any subcollection of this x1, x2, xp, the joint distribution functions would be same as the product of marginals. So, I will illustrate this for the subset x1, x2, xp minus 1. So, let us look at the joint distribution function of x1, x2, xp minus 1. So, which is same as f x1, x2, xp minus 1, x1, x2, xp minus 1. So, to get this marginal distribution function, I have to take the unwanted variable going to infinity. So, the argument of the unwanted variable is xp. I am taking xp going to infinity in the joint distribution function of x1, x2, xp minus 1 and xp. So, that is the result which we saw in the earlier module, that if you have to get a marginal distribution function, you take the argument of unwanted variable going to infinity, and that is what exactly I am doing. Then by 1, the joint distribution function of complete set is same as the product of marginals. So, this is same as this, and limit xp going to infinity is already there. Now, what happens is here only xp is going to infinity and x1, x2, xp minus 1 are fixed. So, I take out the arguments x1, x2, xp minus 1 over here and limit xp going to infinity f xp xp. But f xp xp is a distribution function, and I know that in a distribution function of real variable, if you take the argument going to infinity, I get 1. So, this would be 1. So, this quantity is going to be 1. So, what I get is f of x1, x2, xp minus 1 is exactly same as this. So, we conclude that this is same as this. So, what I saw is if your subset is that of x1, x2, xp minus 1, then the joint distribution function of x1, x2, xp minus 1 is same as product. In fact, you can apply the same argument to show that if you have any arbitrary subcollection of x1, x2, xp, then the joint distribution function of x lambda 1, x lambda 2, x lambda r would be same as the product of marginals. So, this result simplifies our life for checking the independence of random variables. What it says is you look at the complete set. If the joint distribution function is same as the product of marginals, then you can easily conclude that x1, x2, xp are independent. To see this, let us look at this example. So, let xy be a random variable, and suppose this is the joint distribution function. So, which is 0 if x is less than 0 or y less than 0. It is y square if y is between 0 to 1 and x greater than or equal to y. This is x 2 y minus 1 if x is between 0 to y and y is less than 1, x 2 minus x if x is between 0 to 1 and y is greater than or equal to 1, and this is 1 if both of them are greater than or equal to 1. To check whether they are independent or not, I have to check whether this is same as product of marginals or not. So, clearly f x x in this case would be same as limit y going to infinity of f x y x y. So, I have to take y going to infinity. So, my x is fixed. Clearly, if x is less than 0, whatever y may be, it is 0. So, as y goes to infinity, this will be 0. So, this will be 0 if x is less than 0. Now, note that if x is between 0 to 1, and if I take y going to infinity, I get x into 2 minus x. So, this is x into 2 minus x if 0 less than or equal to x less than 1. And if x is greater than or equal to 1 and I take y going to infinity, I get 1. So, f x x turns out to be this quantity. Now, similarly, one can get f y y. In this case, I have to take unwanted variable x going to infinity, f x y x y. And what would be this quantity? Certainly, if y is less than 0, whatever may be the x, this is 0. So, y is less than 0. So, as x goes to infinity, this would be 0. Now, let us look at when y is between 0 to 1. So, which is this quantity. Then for every x greater than or equal to y, the distribution function is y square. So, if I take x going to infinity, then also it remains y square. And clearly, if y is greater than or equal to 1, which is falling over here, and if I take x going to infinity, which falls in the region x greater than or equal to 1, I get this. So, f x x turns out to be this, f y y turns out to be this. Now, you can clearly check that f x y x y is not equal to f x x f y y. That is very easy to check. For example, if x is between 0 to 1 and y is between 0 to 1, and suppose x is less than y, then the distribution function is x 2 minus x into y square, which is not same as x into 2 y minus x. So, this is not satisfied. So, I can conclude that x and y are not independent, and that is what exactly we do over here. This is the marginal distribution function of x, which we obtained as this, marginal distribution function of y, which we obtained as this. Clearly, the joint is not same as the product of marginals. So, x and y are not independent. Now, let us consider another example. Suppose now y have the joint distribution function as this, which is 0 if y is less than 0, irrespective of what x is. But if x is less than 0 and y greater than or equal to 0, then it is given by this. If x is greater than or equal to 0 and y greater than or equal to 0, then this is given by this. So, to check whether they are independent or not, again I find marginals. F x x is limit y going to infinity, f x y x y. So, clearly, if x is less than 0 and I take y going to infinity over here, then this whole quantity 1 plus y e to power minus y goes to 0. So, you get e to power x by 2. If x is greater than or equal to 0, which is falling in this branch, and if I take y going to infinity, which would be covered here. So, I take y going to infinity, again this would be 0. So, I get 2 minus e to power minus x by 2. So, which is the marginal distribution function of x is this. I look at the marginal distribution function of y, which is obtained by taking limit x going to infinity f x y x y. So, clearly, if y is less than 0, this is always 0. If y is greater than or equal to 0, x going to infinity would fall in this branch. So, I take x going to infinity, e to power minus x as x goes to infinity would be 0. So, this would be 2, 2 by 2 would get cancelled, and you would get just this quantity, and that is what you get it over here. So, I get the marginal distribution function of y as this. Now, you can clearly see that f x y x y in this case is same as the product of f x x and f y x y. For example, if y is less than 0, then clearly this is 0, irrespective of what x is. Right. And similarly, you can see in the other branches, if x is less than 0, but y is greater than or equal to 0, then e to power x by 2 multiplied by this quantity, which is same as this quantity. And similarly, in the other branch where x is greater than or equal to 0 and y is greater than or equal to 0, then it would be product of 2 minus e to power minus x by 2, which is this quantity, multiplied by 1 minus 1 plus e to power minus y. So, in this case, we saw that joint distribution function is same as the product of marginals. So, in this case, we can conclude that x and y are independent. So, let me give this as a take home problem. So, let f and g be distribution functions on R. So, they are distribution functions on R. So, that means they satisfy the usual properties of distribution function. I define h 1 x y as minimum of f x and g y. So, these are function in R 2. I define another function h 2 x y, which is maximum of x plus g y minus 1 comma 0. This is again a function in R 2. So that h 1 and h 2 are distribution functions on R 2. So, that means it satisfies all the properties of 2 dimensional distribution functions. Find the marginal distribution function of h 1, which you have to do by taking first limit x going to infinity and then limit y going to infinity, and you have to check whether they are independent or not. Similarly, find the marginal distribution function of S2 and again check for the independence under this model. So, take this as a take home problem. Now, before I end this module, let me give a brief summary of the things I will be doing in the next module. So, in the next module, we will introduce discrete random vectors and study their probability distributions. So, that was all for this module. Thanks for your patience and have a great day.